Hello everybody, I'm going to talk about my poster, which is titled Synthesis and Biochemical Evaluation of Samarium-153 Oxide Nanoparticles Functionalized with iPSMA-Bombesin Heterodimeric Peptide. This research was developed by me, Diana Trujillo, and by the PhD Guillermina Ferro, Enrique Morales, Nayeli Jiménez, Alejandra Ancira, Blanca Ocampo, Clara Santos, Alondra Escudero, Mirna Luna, and Erika Azorin. Something about my abstract. In this research, we report the synthesis and physicochemical characterization of samarium oxide nanoparticles. That nanoparticles were functionalized with the DOTA PESMA inhibitor list 3 bombesin. There is hereafter called iPSMA-Bombesin Heterodimeric Peptide. This system has the evaluation of the effects in their structural, biochemical, and preclinical properties after activation by neutron irradiation. And this system focused for possible use in molecular dual target radiotherapy of hepatocellular carcinoma. Hereafter class ACC. For characterization, we use physicochemical characterization, and that was performed by transmission electron microscopy, TEM, X-ray diffraction, XRD, ultraviolet beam spectroscopy, infrared spectroscopy, thermogravity analysis, TGA, dynamic light scattering, DLS, and Sierra potential. For the biological characterization, we use two cell lines. We use the HEV-G2 cell line, and we use this cell from HCC, and the use were because this cell line had two overexpression of receptor proteins over the surface from the cell, and these protein receptors are the prostatic specific membrane antigen, iPSMA, and the gastrin releasing peptide receptor, GRPR. And another cell line that we could use was PC3. This cell line is positive only for GRPR receptor. So we evaluate our system that consists in samarium oxide 153 nanoparticles functionalized with the iPSMA-Bombesin, and we obtained that system did not present alterations in its physicochemical characteristics after neutron activation, and also show selective affinity and great toxicity in the FG2 cell line with regard to PC3. A little bit of the introduction to understand more this research. What we had in the microenvironment tumor, we have tumor cells or cancer cells, and there are different from normal tissues, normal cells. These cancer cells have overexpression of protein receptor over their surface, and this receptor, like iPSMA, like GRPR, could interact with only selective kind of molecules, and this situation permits us to develop this kind of peptides, like you could see that, like the peptide iPSMA, together with bombesin, and this peptide have the particularity to interact only with tumor cells and not with normal cells. If we could put this peptide over a nanoparticle like samarium oxide nanoparticle, we and those to the system, the nanoparticles accumulate only in tumor microenvironment. If we activate the samarium to samarium radioactive 153, we can use the energy from radioactivity to kill the tumor cells, to damage the tumor cells, and only the tumor cell and not the normal cells. Another thing is the nanoparticles show accumulation in the tumor due to hypereffect. Hypereffect means that in the microenvironment tumor, the endothelial cells are more separate one to another than in normal tissues, in normal tissue. So this greater separation permits the nanoparticles with have size between 20 to 100 nanometers could accumulate into the tumor microenvironment. So these have the chance only the radioactivity could accumulate into the tumor and only interact with tumor cells. All this our team developed this work where use samarium oxide radio nanoparticles functionalized with iPSMA-Bombesin. This is the complete name of our system, and the system was synthesized and characterized for the study of the effects on his structural, biochemical, and preclinical properties. Once activated by neutron irradiation for the possible use in molecular dual target radiotherapy of hepatocellular carcinoma. Well, the method for synthesize this system were very easy. We use the precipitation calcination method. We use samarium oxide natural. We put with chloric acid to form chloride samarium. Then we add sodium hydroxide to form samarium hydroxide, then wash, dry, and calcinate at two temperatures, 600 degrees and 900 degrees. This calcinate did our nanoparticles and natural form of samarium. Then we put our nanoparticles with the peptide, the iPSMA-Bombesin peptide. We put together and we use sodium citrate solution to stabilize our system. And then we use purification to obtain our system do not activate to 153 samarium. For the system activate, we use our natural nanoparticles and we put into the trigamma 3 nuclear reactor. With this condition for 20 hours, we use neutron flux, and then we put our activate nanoparticles into the sodium citrate solution with iPSMA-Bombesin peptide, and we obtain our activate system like it is here. And then we did the physicochemical characterization and biological characterization. For results, we can see the physicochemical characterization. We could see the different size, the different ways of our nanoparticles previous to calcinization with 600 degrees and with 900 degrees calcination and with iPSMA-Bombesin functionalization. We can see from these results that the higher temperature we obtain the larger nanoparticle size, but with higher temperature we have greater crystalline states and purity. So we need to equilibrate the size and crystalline states. Here we can see the TG spectrum, where we can see past samarium hydroxide to samarium oxide. And we can see the very greater crystalline states here at greater temperature from samarium oxide, and this is the exterior spectrum, and we can see we obtain samarium oxides. From the infrared spectrum, we can see two important chains in the Bauerland, where we can see bands at 1542 and 1443. To move to higher, Bauerland moved to 1517 and lower 1401 Wavelengths in D, and this change to move to high to lowers and lowers to highs, it's in the case of a monodentate interaction of the samarium atoms on the surface from the nanoparticles with the part DOTA from our heterodimeric peptide. Finally, in the ultraviolet visible spectrum, we can see one band at 233 nanometers from C move to a slight blue shift in D, and that is indicating of change in chemical environment. For biological characterization, we did the cell viability, where we can see more viability in FG2 and more viability in the cells with protein interaction with nanoparticles activate to 150 samarium, but without the peptide. And we can see with the functionalized with the peptide, the viability is lower. And in the 2 hours and 24 hours and 72 hours. And we can see a little bit more viability in PC3, and that is because PC3 only have one receptor. The same behavior we can see in the analysis of proliferation and proliferation analysis. Then we can see more proliferation when in the cells when only samarium oxide nanoparticles than the samarium oxide nanoparticles functionalize with the iPSMA-Bombesin. And the difference between FG2 and PC3 is the same. For cell internalization, we can see the same effect. We can see more internalization with the samarium oxide nanoparticles functionalized with the peptide iPSMA-Bombesin than the nanoparticles without functionalization. We we did the evaluation of the biodistribution. We evaluate different tissues like blood, hair, lung, liver, and the evaluation was development in different times. And we can see in all times the greater accumulation were in liver. This is well because the system is focused to hepatocellular carcinoma. One important thing that we could see was our system have luminescence properties. We can obtain optical imaging by its luminescent properties. And of these results give us to our conclusion that were the higher affinity and cytotoxicity produced by our system was observed in the cell line HEV-G2 because they overspread both receptors, PESMA and GRPR. Also, conclusion was the samarium oxide nanoparticles show physicochemical properties that allow their neutron activation and functionalization with iPSMA-Bombesin. The other conclusion was that these results validate future clinical studies for the evaluation of dosimetry, therapeutic efficacy, and molecular imaging in vivo. And finally, the last conclusion was that our system show luminescent properties induced by the interaction of ionizing radiation with the atoms of the nanoparticles. These phenomena allow the acquisition of both nuclear and optical imaging, nuclear for samarium 153, and optical imaging for this phenomenon of luminescence. And of this give us a future perspective, such as the development of new nanoradiopharmaceutical based on radiolantanides.